Hi, my name is Emmanuel Schanzer, and I work with an organization called Bootstrap based at Brown University. I'm going to be talking to you about adapting student IDEs for blind programmers. And throughout the talk, you'll hear me use the abbreviation VI to stand for both programmers that are completely blind as well as programmers that have strong visual impairments. My co-authors on the work are Sina Bahram from Prime Access Consulting and Professor Shriram Krishnamurthi, also from Bootstrap and Brown University. Bootstrap serves as a good use case for this work. It has meaningful scale. It's a nationwide CS education program reaching tens of thousands of students each year. So we've run into many of the challenges and constraints that others may face. In addition, it's a meaningful sample. The majority of our students are in high poverty schools, which means that teachers don't have the ability to purchase, download, and install custom software. Our IDE has to live entirely on the web. In addition, these schools lack the funding to purchase specialized equipment like Braille output displays. So the only assistive technology that we can rely on are screen readers. We view accessible IDEs as a three-layer problem. The first is how to make the IDE navigable for VI users. The second is how to make sure that a screen reader is verbalizing the output of programs appropriately. And finally, that the assistive technology is providing verbal cues that assist in the navigation, comprehension, editing, and writing of code. Let's consider navigation first. The user interface of our IDE has three main regions. There's a toolbar that has a bunch of buttons on it. There's a text area for the source code of the program, and there's also a REPL. If you're programming for accessibility on the web, you're probably very familiar with the ARIA standards. These specify how to annotate different elements, how to prioritize announcements for the screen reader, and so on. In our environment, all buttons and UI elements have ARIA annotations, as well as appropriate key bindings. For example, a VI user who focuses on the run button, what they'll hear the screen reader say is, run the program F7. Now, there are some user interface conventions that aren't specified by ARIA, and in this situation, we borrow community-approved conventions. The Chatzilla chat client has established a number of these. It has excellent accessibility support. One example of these is the focus carousel. Pressing F6 repeatedly in Chatzilla shifts focus to the major regions of the app, and we've implemented this in our IDE as well. A student who presses F6 repeatedly in our IDE will find the focus rotating between the REPL, the source code, the toolbar, and back. Let's consider the navigation challenge of the REPL itself. A REPL can be thought of as a conversation. The user types in a program, the IDE evaluates the program and prints out the result, or prints out an error message. And we can borrow UI conventions for navigating conversations, again, from Chatzilla. Alt page up and alt page down can be used to read the previous interaction or the subsequent interaction. And when reading these interactions, of course, the screen reader needs to verbalize what the program output was. And this brings us to the second problem. How do you verbalize output? Now, even simple and textual output is fairly tricky. Consider three different programs that spit out three different results. There's the number 3, the string containing the character 3, or a string containing the actual word 3. A sighted user, by looking at the output, can immediately see that these mean three very different things. But if the values themselves are simply passed to a screen reader, a VI user is going to hear the screen reader vocalize the same thing for all three outputs, 3, 3, and 3. And this is obviously a problem. What we've done is annotated our numbers, our strings, and our Booleans so that they have special ARIA labels that a screen reader can pick up. A VI user, for example, will hear 3, a number, 3, a string, and then depending on the settings they've implemented in their screen reader, it might read 3, a string for the third value, or even THREE, a string for that value. You may notice that we've chosen to put the value first and the data type second. This follows some conventions for semantic prioritization, prior work done by Stefik and his team in 2009. But what about more complex output? What about structured output? So for example, our environment has vectors and lists. A VI user who's hearing these vocalized would hear something like a vector of size 3, true, a Boolean, hello, a string, 4, a number. Or they might hear a list of length 5, 1, a number, 2, a number, and so on. So how do we arrive at this? Well, this requires building in accessibility at the runtime level so that every possible data type is labeled properly with a descriptive ARIA label. Now, there's room for future work here. For example, navigating larger lists or deeper trees probably requires something more sophisticated, and we could consider generators. For example, a VI user might hear a list of 10,000 elements, press the right arrow to hear the next 10, the left arrow to hear the previous 10. But what about image output? Well, our runtime uses scene graphs to compose images. So you may have a scene graph that specifies a triangle that's been rotated and overlaid on top of a rectangle. And when this graph is flattened, all of these are composed to produce the final output image. So how do we make that accessible? What we've done is annotated the graph, essentially creating a sentence diagram for every image. When the graph is collapsed, not only do we get the final image, but we also get a complete final annotation produced alongside that image, which we can then hand to the screen reader. So, for example, a VI user might hear read aloud a solid red equilateral triangle with sides of length 20, or a solid red equilateral triangle with sides of length 20, rotated 45 degrees on top of a solid green circle of radius 4. Now, the big takeaway here is that if you're serious about accessibility, you need to roll your own runtime because you want to preserve as many of the semantics as possible throughout the processing pipeline, such that a screen reader has access to something useful to vocalize. Describing colors is another interesting challenge. Our environment uses the X11 color palette, and so there are a number of colors that simply have names. So a student who specifies that a circle is green, well, we can pass that word green over to the screen reader. However, what about programmatically created colors, right? Arbitrary values. Vocalizing the hex values for R, G, and B, for example, isn't terribly useful. So let's consider this in one dimension, say a gradient that goes from dark red to medium red to light red. An arbitrary point on this gradient can be vocalized by finding the nearest named neighbor and passing that name to the screen reader. And this generalizes to any number of dimensions. So you could imagine a three-dimensional color space with axes for R, G, and B. Each of the X11 colors exists as a point in this space. And for any arbitrarily defined point, well, we find the nearest named color and use that. Now, color theory tells us that there's actually a lot of different color spaces we could use. And we've chosen to implement this using the LAB color space, which most closely mirrors the way the human eye perceives color. This has an added benefit of having the word that a screen reader chooses most closely matching the word that a sighted user might choose themselves to describe that color. VI students working alongside sighted students are much more likely to hear the same output. But what about describing imported images? Suppose there's a program whose output is the image of a puppy. In this situation, we use Google's Vision API. We pass that image up to the cloud, the Vision API produces its best guess for a description of the image, and we pass that along to the screen reader. Now at this point, we're able to vocalize lots and lots of different possible static images, whether they're programmatically composed, arbitrarily imported images, and so on. But there's plenty of future work to be done. For example, describing animations by vocalizing each frame entirely is not very efficient. It would be much better instead to describe these animations by verbalizing only the differences between scene graphs. Let's consider the final challenge, writing code. Well-formed programs are abstract syntax trees, and sighted users have to sort of see these trees as they're writing code. And we rely on lots of visual cues to do this. There's syntax coloring, auto-indenting, bracket matching, and so on. But VI users don't have access to these visual cues, and so hearing the screen reader read the line number aloud is not as useful as it could be. Instead, it would be far better to navigate the AST directly. Users can recursively descend and ascend in a semantically meaningful way. Baker, Milne, and Ladner in 2015 proved that lots of VI users experience substantial improvements to program navigation, comprehension, and orientation. But there is one problem. A single syntax error can bring the whole thing crashing down. If we can't parse, we don't get the tree. And this is where we can exploit the property of the language that we've chosen to use. Bicameral languages, like Racket, for example, have a distinction between well-formedness and validity. We can use matched parentheses, similar to XML's open and closing tags, to ensure that a program has a certain level of well-formedness, right? Each of the parentheses are at least matched, even if what's inside those parentheses isn't necessarily valid. This is a much more permissive rule for parsing, which allows us to construct a tree. And VI users navigate this tree using the exact same key combinations they might use to navigate a file system. We render these as blocks in the browser's DOM, which can be navigated and modified using these key shortcuts, or even dragged and dropped by sighted users. There's a couple of lessons that we've learned from working with students with this IDE. Daniela Marketu invited us to participate in the Alabama STEM Wars event, an engineering-focused event for students with disabilities. And we have here a photograph of some teachers who got really into it. They dressed up as stormtroopers. It's a lot of fun. And we ran the computer programming event at STEM Wars. We learned a couple of things. First, not every student is familiar with screen readers, and we were surprised to hear that we needed to spend a lot of time training them on the screen readers themselves before showing them the technology. We also found that while the technology was nice for longer programs, shorter programs really didn't need it. In fact, it got in the way. This is likely because students who have, decent short-term memory are able to just think about the program as text without needing to hear the structure. Finally, the most surprising outcome was that students especially loved making images, and this was something of a shock to us. For students who were born blind, for example, who have no notion of what a purple star looks like, why would they be so engaged and excited about making one? One of the teachers who worked with blind students explained. Even when these students are included in a mainstream class, they're often given blind work that's different from the work given to sighted kids, and they feel that. So being able to write programs that generate the same output that their sighted peers would write was really powerful for these students. We've learned a lot, and we have a lot of people to thank. Especially want to thank Andrea Stefik, Vince Cerf, Richard Ladner, and Daniela Margetu for all of their support. Finally, if you'd like to reach out to us, our email addresses are here on the final slide. We thank you for your time.